Yes.
Okay. All right.
Whatever. Yeah.
Oh, yep.
Sorry.
Go ahead. Perfect. Okay. This is black. This is black. I'm gonna keep that here. And oh, this one is very nice. This one's good. This one. Hey, how's it going?
I'm fine, you?
Yeah, good, good, good. Those are the mugs, are they?
Yeah, yeah.
Oh, nice.
Did you get one?
No, but I mean, I want to give priority to the young people,
yeah,
of
yeah,
course. So, yeah. Hey, good morning. Hey, hey, yeah. Sorry, man. Thanks. Yeah, they gave me a new one, but I think they'll still be very happy with the old one. Thanks.
I think so, yeah.
I arrived at the hotel. I'm like, shit. No.
You were thinking that you were sleeping on the street, maybe.
Yeah, I was very tired. You know, it was like 3 a.m. for me in my.
So you were
in my,
walking or you took the subway?
I took the metro. Yeah.
Ah, okay.
This guy. He showed me all the tricks. You know, which car to get on so that you stop exactly in front of the stairs and you can be ahead of the crowd.
Oh, you took the subway together?
Yeah.
Yeah,
Yeah,
you took,
It was late at night, so it was.
Yeah, yeah. And this morning I tried to replicate it, but I failed horribly. And I was behind the whole crowd on the stairs, so I now understand why.
Hector have a lot of techniques.
Yeah, he knows all the pro tips. It's crazy.
But isn't there? He has a tour, non-commutative tour. Explain that already.
No.
Yeah?
I mean, he explained, maybe that's what the non-commutative tour is. How you can take the bus back, but only pay for one.
Yeah, that's one of the
No, but it's one small part of it because he have a huge story about Santiago.
just about from nowhere. I don't know where.
Ah, that's great. That's great. You should write a paper on this, I think. Yeah.
Do you have a mug?
Do I have a mug? No, no. But I mean, I feel like, oh, is that right? I feel like the young people have priority though. But I'm curious to see it at least. Right, let me check it out. Wow, that's actually
Met your expectations?
very nice. Very nice mug. It looks kind of vaguely medical almost,
Yeah,
the logo.
yeah,
I don't know why, but
that's
it
true.
gives
That's
me a
true, now that you
medical
say
vibe. Yeah. Well, that's pretty cool.
Yeah, and it has a little spoon also.
Okay. But are you sure I can take it?
Yeah, I think
Because
so.
the junior people maybe
No
should
one
get
give me any
priority.
restriction. I'm giving up.
I'm very
mugs,
happy
so-
to take it. Yeah, I love mugs. So.
Quizás recordar el asado de mañana después de
Okay.
Y que, ay, dile que sí. Si lo vienen a ver.
So good morning, everybody. I think we're in time, right?
Sure.
So before the next session of Jan, the organizers reminded me to remind you that tomorrow there is the asado. And of course, precondition to participate is that you come to the talks in the morning. Serious. Okay, so yeah, so I'll
Okay.
yeah, thanks.
Thanks very much. Okay, so today I'm going to continue the story where I left it last time, and I gave you a sort of a sneak peek of the origins of the famous and celebrated work of Gros and Zagier by showing you Zagier's letter. And today I'll tell you a little bit more about what that work entails, and this will be our exploration of some of the aspects of CM theory that will later on try and generalize or extend to real quadratic fields. And so I'd like to begin with just a little bit of motivation coming from the fact that, so whenever we have E over Q, an elliptic curve, we know by the Mordell-Weil theorem that the set of rational points on this elliptic curve carries a group structure, but it's not just any group, it's in fact a finitely generated group, and that means that it can always be written as some finite torsion group, which I'll call T, times a number of copies of Z, and the number of copies is traditionally called the rank. Yeah? So there's two things that I could discuss in this context, namely what is this rank and what is this torsion, and they're both very interesting stories, but I'll just say that the possibilities for this torsion are finite, so the possible groups T that can occur, have been classified fully classified in a groundbreaking series of papers culminating in this 1977 paper on the Eisenstein ideal by Barry Mazur. So we know there's a finite set of possibilities. I could write it down, but it's not going to matter for a talk of what this structure of this torsion group T can be. The rank, on the other hand, is much more mysterious, and we don't know what all the possibilities are for the rank. But the Burchell-Swinnerton-Dyer conjecture at least gives us, conjecturally, an analytic handle on this rank. And as most of you will know, it states that this rank R that appears here in the exponent of this Mordell-Weil group is actually equal to the order of vanishing at s is equal to 1 of the L function associated to this elliptic curve. Sorry, see the people in the back struggling when I write low. Is this visible for everyone? Not really. Okay, I'll try and stay away from the low end of the board as much as possible. Okay, so this conjecture, of course, is widely open. We know a lot, certainly, but in general, we don't really know how to prove such a thing. And one of the difficult parts is how do you construct systematically a supply of rational points on some random elliptic curve? And the main method that we use for this is we make use of the fact that elliptic curves over Q are modular, which means that we can always consider the upper half plane, which henceforth I will denote by H. And we can consider the quotient using the left action of the group SL2Z by linear fractional transformations, and the subgroup gamma 0 of n, if we quotient that out, we get an affine curve, which, when compactified, is commonly referred to as x naught of n. So if you take this quotient, of course, you're missing a couple of points. You're missing the cusps. But if you compactify it, you get x naught of n. And it's now a theorem that any elliptic curve over the rational numbers, as on the left-hand side board, admits a finite map, a non-constant map, from such a modular curve x naught of n for an appropriate value of n. And in fact, n can always be taken to be the conductor of E. And this is kind of the only systematic strategy that we have for constructing rational points on E. If we find some interesting set of points in the upper half plane, we can map them through to x naught of n and then map them to the elliptic curve and hope that they're algebraic. And in fact, that's precisely what CM theory does for us. Now, this may seem like a bit of a miracle because, of course, this map is a nice algebraic map, but this map is a highly transcendental map. So all of the functions involved here are just analytic functions. So if I take some algebraic point here that satisfies an equation, I don't expect in general that the image after I apply this analytic map will still be algebraic. But this is true for CM points, and this is the miracle of CM theory. And so in general, the way you work this out is via the Shimura reciprocity law, which sort of subsumes all of the things that I told you about yesterday, specific cases like the J function, these elliptic units, all of these things that I discussed yesterday are all special cases of the following very general procedure to describe the field of rationality of this procedure that I just told you about, where you map CM points to points on x naught of n. Okay, so pick, let's say, a primitive, and I'll tell you in a second what that means, quadratic form. Let's call it QXY, and I'll tell you a little bit more systematically about the theory of quadratic forms at the end of today's lecture, specifically for the case where the discriminant is positive, where we will use some reduction theory in what follows. So we pick such a primitive form. A primitive means that the greatest common divisor of A, B, and C, all of which are assumed to be integers, is 1. So they're coprime. And I will also assume that the discriminant, b squared minus 4ac, is a negative number. It's a negative integer. Okay. Now, if I have such a quadratic form, I can consider its root. So, in fact, there's a distinguished one, which I'll call tau. And tau will be the root that I obtain where I put the plus sign here in the quadratic formula. So this one. And in fact, so in addition to this hypothesis, let me also assume that A is greater than 0, because I might as well. Now in this case, this tau is a point in the upper half plane. That's by this assumption that delta is negative, so this is indeed something with a non-trivial imaginary part, and that imaginary part is positive. Yeah? So this is what we call a root of this quadratic form. Now, with all this data, we're going to define a unique embedding let's call it eta sub q. And this embedding will be a ring embedding from the field K, which is defined to be the field that I obtain if I adjoin this root tau to the field of rational numbers Q. And I'm going to embed it into the set of, or the algebra of 2 by 2 matrices with coefficients in Q. Yeah? And this will be a ring embedding. And this ring embedding is characterized uniquely by the property that if I take some element alpha in my field K, and I map it to the corresponding matrix using this eta, so that's eta Q of alpha, And now I make it act. It's a 2 by 2 matrix, so I can make it act on the column vector with coordinates tau and 1. Then that will be the same as the multiple of that same vector, where that multiple is exactly the element alpha that I started off with. So in other words, tau 1 is an eigenvector for this matrix, and the eigenvalue is precisely alpha. Okay? So this uniquely characterizes this embedding, but we can also make it very explicit. So explicitly, it is given by, if I take a to q and I apply it to an element in k, and a general element of k can be written in the form x plus ay tau. Yeah. Okay, this a didn't need to be there a priori. I could just write it as x plus y tau, where x and y are rational numbers. But for normalization purposes later on, this will be a little bit nicer. So I'm going to normalize my y so that it's a times y appearing here. So on such an element, if I tell you where that goes, so which matrix that is mapped to, it's a very explicit formula. So it's x minus by and x on the diagonal. And then here I get minus cy and ay. So that's an alternative description of the map. I'm just telling you what this embedding is. And now you can verify that it satisfies this indeedly. And then, so this is characterized by it. Okay, so we have this embedding. Now, one thing to note maybe about this. So I'll write this as a remark here. So note. If I inspect all of the elements appearing in this matrix, I come to the conclusion that if I take the quadratic order of discriminant delta, which, so the order determined here by this tau, which I'll denote by O delta, and it's just obtained by adjoining to Z the element A times tau. This is a quadratic order. Here I need this A, and that's also the reason I normalized it here with this A. If I apply it to such an element, so that means that x and y are both integers, then I see that I get an integral matrix. So it's a simple observation. So this O delta maps inside of M2Z. All of the denominators are trivial. Okay. All right. Here it is. Okay, so maybe I'll leave that picture up there actually, and just erase this. That should be enough space. The Shimura reciprocity law, which essentially you get by elaborating on the theorems of Kronecker that I stated last time, elaborated quite a bit, but nonetheless, the essential content is there, as was discovered by Shimura. We now get a commutative diagram. So this is a highly non-trivial theorem I'm about to state, the commutativity of this diagram. Well, and the properties that it has that I'm about to state. So we get a commutative diagram involving this embedding and the natural extension to the finite adels that I get from it. So on the one hand, I'm going to put my field K, and now I'm going to take the finite adels of K, which I'll denote by K hat, and I'll take K hat star. So it's the finite adels. So meaning I take Z, I take the profinite completion, Z hat, and then I tensor with K. That's what that is. And then I take the units. Okay, so now I can take an element in here. I can take this map. It naturally extends to a map from this K hat. And I can keep track of two things. I can keep track of tau, and I can keep track of this completion of this A to Q in here. And this tau will be, well, upper or lower half plane. In fact, I normalized it there with this assumption to be in the upper half plane, but that wasn't really necessary. You can carry this over in general. And now, because I've taken the units, you see, I land not just in M2Q hat, but in GL2Q hat. So the units that I get over there. Yeah. So I get a map like so. I can also take the quotient by the global elements in K. So I can quotient that by K star on the left. And of course, if I do that, I also have to quotient by something here, and I'm going to quotient precisely by GL2Q on the left here. Yeah? So that changes this map precisely because the image of K inside of this lands inside of M2Q, so K star lands inside of GL2Q. And here if I change by multiplication by K, of course this condition will also change, and the change is precisely by linear fractional transformations on K. So that's why you get a map like so, where GL2Q acts by linear fractional transformations here, and just by translation there. Okay? All right. Now, there's two things to note about this. The thing on the left-hand side, class field theory tells us that there's a very concrete way of thinking about this. In fact, this is isomorphic via the Artin map over K to the Galois group of the maximal abelian extension of K over K. It's a very deep statement. It's class field theory. And so this Artin map, it just takes a uniformizer at a finite place, let's say, to the Frobenius element in this extension. And that, in fact, defines it. The fact that that's an isomorphism is a very deep theorem. So, in fact, for normalization purposes, it's a bit better to take the inverse of the Artin map. So the Artin map composed with inversion. But that's just a detail you don't have to worry too much about. Now, on the right-hand side, we've now created a map from this Galois group to this space. This space really is the universal space by which I can now take quotients to get an adelic description of modular curves. And for any compact open that I take, U, GL2Z hat, let's say, I get a corresponding quotient. So this is in GL2Z hat. I get a corresponding quotient which is an affine modular curve. Yeah? So it's usually called Y of U, and I'm just getting the C points, like so. Okay, so if I follow this isomorphism and then I go along like this, of course, by definition, I get a commutative diagram where there's a map phi here that goes from the Galois group of the maximal abelian extension of K to the points of this modular curve. Yeah? And this is true for any U, so I can vary U later on. That's perfectly fine. Yeah. Okay, so now the theorem, the commutativity wasn't very deep because I defined it to be commutative. But the theorem is that the image of phi, it doesn't just land on some random complex points there. This has a canonical structure of an algebraic curve, and in fact, the image of this phi lies in the points that are defined over the maximal abelian extension. So they're not just algebraic, they lie in some abelian extension of K. So that's a very specific theorem. Moreover, if they lie here, there's also an action of the Galois group on this set, the Galois group of K ab over K. And of course, there's an action of the Galois group of K ab over K on this thing on the left, just by multiplication. And that makes this map phi equivariant. So, and this is an important and, phi is equivariant, equivariant from gal K ab over K. And yes? Sorry? A YU of C. So this YU is the algebraic curve that I get by taking this quotient by this compact open that I've chosen in GL2Z hat. And it depends strongly on what U is. Yeah? Also its rationality structure will depend on that. And that's what YU is. So this algebraic curve has a set of C points. Yeah, and that's what I'm mapping to. Yeah? So this is really, this YU of C, it's this part of the picture. Yeah? Or at least the affine part of this curve. It's really an open Riemann surface. Yeah.
This tau really is just this tau fixed, one fixed tau in this map.
Yeah, exactly. So you take your quadratic form, indeed, yeah, tau and q. Of course, if you translate by k, you're going to change tau and q, and in the same way.
What when you translate?
When you translate by k, because that embedding is sort of characterized by this property, and if I translate by k, this property will get messed up. So I have to change tau, and that's why the GL2q is acting here on the h plus or minus 1. Indeed, Yeah, but you pick one, and then that's a well-defined notion. Okay, so we now know that we've constructed points that are algebraic out of this map. And this is completely general, so I can still pick my u, and I can pick my quadratic form somewhat freely, and out comes some algebraic point. Precisely where it's going to be algebraic, etc., that still remains an exercise, but essentially this commutative diagram together with these two statements imply everything. And as difficult as this is to prove, it's quite nice to use in practice. And so for this specific case, it's worth pointing out exactly what it says and what the field of rationality is of the points that you get out of this construction. And in that situation, you call them Heegner points. Yes?
So this map, are you saying that this is kind of independent of the quadratic form you choose? I just want to
Well, the base point will change if you change your quadratic form. Yeah. So the map phi is not independent of that choice. Yeah. But you pick a representative. Let me spell it out for the x naught of n. I think it'll be clearer once I tell you how to do this calculation. Oh, maybe I should have kept the matrix, actually. That was not so smart. But OK, I hope you remember it, and otherwise we can write it down again. Okay, so... Sorry, say again?
The quadratic form.
Exactly. So if I hadn't put this quotient, this would be perfectly, everything would be fixed. Yeah. Yeah. Okay. All right, so example. And of course, nothing stands in your way to do a different example and take your favorite modular curve, some non-split Cartan modular curve, or whatever you like. But the classical situation that is of great arithmetic interest for what I'm about to say is where you pick this compact open U to consist of matrices A, B, C, D. Yeah, so A, B, C, D are all in Z hat. Yeah, so this is in GL2 Z hat, such that C is divisible by some fixed integer n. Think this kind of n. Yeah? So I fix an n, and I take this compact open, and then indeed this yu will literally be the affine part of this classical modular curve, x naught of n. It's just an adelic viewpoint, but nothing else is really going on. So then yu is better known as y0 of n. Okay, so now when Q is a Heegner form, so we're going to put some condition now in our Q. And a Heegner form means that n divides the first coefficient of this quadratic form, a. So like so. Then the corresponding CM point is very special. We call it P sub Q. It's in y0 of n of k delta. Now, I'll remind you what the effect of eta was. So that's x plus ay tau. That was x minus by, because unfortunately I erased it, so I have to rewrite it. So x, ay, and minus cy, I think. Yes. Okay. So it's this formula. So now we see, before we made an observation, which I raised here, which was to note that the quadratic order would always land inside of M2Z. But now a little bit more is true, you see. Because if I have a Heegner form, and I look at this entry, not only will this be an integer, it'll be an integer divisible by n. Yeah? And of course, adelically, the same remains true. So this means that the image will land inside of this U. So it's not just integral, it'll actually land inside of this U. So it follows from the Shimura reciprocity law stated there that in fact this point will be acted trivially upon by anything in the profinite completion of this order O delta. Yeah? So where K delta is precisely that, which is by definition of the ring class field. So I'll just say it's the ring class field, and then I'll tell you what that means. Of discriminant delta. That means it's uniquely characterized by class field theory by the property that the Galois group corresponds via the Artin map to K hat star modulo K star and then modulo the profinite completion of this ring. Yeah? So this is a finite group. And you can see now why this is true, because if I, of course, change by anything in here, inside of the profinite completion of O delta, I'm just going to be changing by U on the right, which means that here, of course, that will make a change, but in the quotient it won't. It will actually land in the same point. And so therefore, if I go all the way back in this diagram, I see that the part of the Galois group that is described by this profinite completion of O delta star acts trivially. So therefore, this is really the field of definition of this point. Yeah? And in fact, you can often also argue that it's not defined over a smaller field. So this P of Q now, miraculously, so it came from an algebraic point in here. We mapped it over here to our P of Q. It's still an algebraic point, but I would love to go to my elliptic curve and get something that's rational, not just over this K delta, but maybe over Q. And at least we can start with K and see where we go from there. Yes?
What do you mean by the CM point corresponding to a quadratic form?
Yeah, so, right. So if I take my quadratic form, let's fix it for now. I can take this root tau, which lies here in the upper half plane, and now I can follow it through in this uniformization, which is really the complex analytic incarnation of this map here. Yeah? That's what I've called PQ. So that's what the CM point is related to that. And if I change my tau by anything in this group, gamma 0 of n, that's not going to affect the image. Yeah? And this is something we noticed here. And now, if I act on it by the Galois group, that's not going to be affected as long as I stay inside of this compact open. So therefore, this point is really defined over this finite extension of K. It's a finite abelian extension. Okay? All right, so from this PQ, of course it lies on a curve, but I can view it inside of its Jacobian and now just add them all up, all the Galois conjugates, because of course this will also tell me that the Galois conjugates will be accounted for by points of the same discriminant. So I can take all of the equivalence classes of a fixed discriminant, add them all up, and then I know that I'm really fixed by the entire Galois group, because I'm just shuffling them around via this reciprocity map. And so this is what I'll call P sub K. Maybe I should call it P sub delta, actually, because I haven't assumed anything that the discriminant is fundamental. And what that is, it's just a sum of all Q's whose discriminant is delta of this point PQ, and then I subtract the cusp infinity. This is a degree 0 divisor on the Jacobian, and I add them all up. This is a finite sum. And so this will be in J naught of n K by the Shimura reciprocity law. Yeah? So no longer K delta, but really K, this imaginary quadratic field. So this is called a Heegner point. And of course, it's great to construct points that are almost rational. Yeah, they're in K, this imaginary quadratic extension of Q. But we could have constructed the trivial point. Yeah, we don't know that at this point. So a very natural question that arises is, if I pick some delta, is this P delta torsion or not? Can it generate some of the rank of the Jacobian or not? And we can also fine-tune this question. We can ask, what are the arithmetic properties of these P deltas? How do they interact with each other arithmetically? And one way to make that precise is to ask what their height pairing is, and that's precisely what Gross and Zagier did. So all of these questions were attacked by Gross and Zagier.
When you write infinity, you fix one cusp or one?
Yeah, so I picked the cusp infinity here, but you could pick another cusp as well. And the difference would just be a cuspidal divisor, which is by Mann and Drinfeld always a torsion point. So it wouldn't really affect much anything that I'm going to say. So if you prefer a different cusp than infinity, you're free to pick it. Yeah.
No, it's just a question. If you move it with PQ or if you fix just one once?
Ah, yeah, no, so I pick the same one for all of them, yes. That's the cleanest, yeah, absolutely. But it doesn't really matter all that much, yeah, sorry, yes.
It's not yet on the elliptic curve, though, right?
No, it's not yet on the elliptic curve, it's better actually, it's on the Jacobian still. So I can then analyze it in the Jacobian first before I map it to the elliptic curve. Yeah? So the elliptic curve sits inside of my Jacobian, but it's much bigger in general. Here in my picture, it's 2 dimensions bigger than the elliptic curve, because this is a genus 3 curve in my picture. Yeah. But
Stupid question.
yes.
before you raise. I'm not sure I understand what this map tau is.
Oh, tau, right. You send it to the fixed point really of this. Yeah? And then you're gonna, so tau, before I take this quotient, you send it to the fixed point tau from my fixed quadratic form. So it doesn't move at all. Yeah. But then when I start moving k, both aspects are going to start moving. So it's only on the equivalence class here, but I pick a representative tau, and in the end...
but in this picture, k is not moving, it's fixed, right? I mean, what?
k is fixed, yeah,
Yeah,
absolutely.
so then tau is one.
Yeah, absolutely,
number.
yeah, it's one number.
Fixed.
Yeah, it's fixed, absolutely. Yeah.
It's not a map, so to speak.
It's not a map, no, exactly. So it's a constant map, yeah. Absolutely. It was constant before, and then it was constant after.
What do you mean by p delta can be a trivial point?
So p delta, so this is, so I stated before for the elliptic curve that the Mordell-Weil group is finitely, sorry, I'm not sure who I'm looking at. Oh yeah, there, okay. I stated before that the Mordell-Weil group is finitely generated. The same is true for any abelian variety defined over a number field. So this is an abelian variety defined over Q. In particular, this is some finitely generated group. It has a torsion part and has a free part. And I'm wondering whether this construction that we made, as clever as it may have seemed, perhaps always constructs some torsion point in the Jacobian. And then it wouldn't be very interesting because it wouldn't help us much for the BSD conjecture.
So your trivial point means the torsion point.
Yeah, exactly. So, I mean, it could also be trivial, right? That's even worse. Yeah? But in general, if it's torsion, we also don't gain much from it. Yeah? Okay. Now let me tell you what Gross and Zagier did in a nutshell. And I'll try and single out the steps that will be of importance to us later. It's a phenomenal kind of work, and there's been a lot of follow-up work since then, and you could easily spend a semester or longer on this paper. But I just want to highlight a couple of aspects of the work, as well as what I think are the key conceptual steps in the whole proof. And so all of this is due to Gross and Zagier. It all started with that letter I showed you yesterday. And then, in fact, the setup I'll talk about today mostly is due to Gross, Conan, and Zagier 1 year later. But they're very closely related, of course. So what Gross, Conan, and Zagier do roughly can be broken up into 3 steps. So they try and address these questions that we raised about this p deltas. Are they always trivial or are they not trivial? How do they relate to each other if I change the delta? And they try and do it by interpreting all my questions from before as questions about the height pairing of these 2 points. So what Gross and Zagier calculate explicitly is when I take p of delta 1 and p of delta 2, where delta 1 and delta 2 in their paper are fundamental and co-prime discriminants. Yeah. Delta 1 can also be equal to delta 2, and that's this paper. If they're co-prime, that's this paper. But the ideas are very related. Okay? All right, so you have these 2 points on the Jacobian. And what you can try and do is compute their height pairing over a common field of definition. Yeah? So it's the neuron height pairing on the Jacobian, and it's a number. And it sort of measures how the 2 interact with each other. Yeah? This neuron height pairing, which you may be familiar with in the case of elliptic curves, works very much the same way for abelian varieties. And what they do is they very cleverly analyze how it breaks up into infinitely many parts, but broadly speaking, 2 conceptually very different bits. Okay, so I'll tell you in a second what all these symbols mean. Okay. All right, so when we learn about height pairings, for instance in Silverman's book on elliptic curves, we learn that there's a globally defined height pairing. So this is some number, some real number that doesn't really have any additional properties. But it breaks up as a sum of contributions at all of the places of the number field that my cycles are defined over. So there's the infinite places and the finite places. So there's a contribution at infinity, which is kind of an analytic contribution. And so it typically takes the form of some Green's function. And then there's a finite part, which is much more algebrogeometric in nature. And so it involves in particular this kind of MQ, which is an intersection number. So let me write it like here. So it's an intersection number in the arithmetic sense of the 2 points. Yeah? Meaning you're going to reduce the 2 points mod Q. And you're going to measure how much they look like each other by measuring the number of powers of Q that divide the difference, roughly speaking. Yeah? So it's an arithmetic intersection number in that sense. And so by definition this is true. Yeah? So they have this Néron height pairing, which is some mysterious number, but it breaks up into this concrete infinite sum of local contributions. And this is what they calculate explicitly. Yeah? So they find explicit formulae for this intersection number in elementary terms. And crucially, they also give an automorphic description of this Green's function, which in general is quite a mysterious thing. Yeah? So I won't say too much about this in general. There's a lot to say about it. But I'll take the special case n equals to 1 later, and then I'll tell you what all the terms are. Yeah? Okay, so this is conceptually the first step of their paper. And it's a big chunk of the paper also somehow. I mean, this is not an easy calculation at all. It takes many, many pages to compute both sides. In fact, most of the paper is devoted to this. So they want explicit expressions, horrible but very explicit expressions for all of these quantities involved. Yeah? Okay, so maybe I'll say just a tiny amount more about what the MQs are. So the MQ is, like I said, this arithmetic intersection number. They recast it in a way that I'll make explicit later on in the real quadratic case, my final lecture this week, so arithmetic intersection number. They recast it as a counting problem of embeddings into quaternion algebras. So this is their kind of insight, is that these can be counted using embeddings of the two imaginary quadratic fields that I get from the two negative discriminants that I took inside of not M2Q, but rather a quaternion algebra ramified at Q and infinity. And if you've read Silverman's book, you can kind of see where such a quaternion algebra might come from. And the key is that if you have two different discriminants that reduce mod Q, these 2 points reduce mod Q to the same point, then that means that the CM elliptic curves that are associated to them have the same reduction mod Q. But these CM elliptic curves have CM by totally different orders. Yeah? One is an order of discriminant delta 1 and the other is an order of discriminant delta 2. So they have nothing to do with each other. But this reduction map is common. So it injects the endomorphism rings into the endomorphism ring of the reduction mod Q. And because they're different orders, there has to be enough space in the endomorphism ring of the reduction mod Q. And the only possibility is that they're both supersingular at Q. And the endomorphism ring of a supersingular elliptic curve is precisely a maximal order in this quaternion algebra. So that's where the link comes from. It feels very magical at this point, but that's where they obtain this link. So you start with embeddings of K1 and K2 in M2Q, but you obtain embeddings into a different quaternion algebra, and that was really a key insight in their work. Okay, but I'll say more about this when we get to it in the real quadratic setting. Okay, so once they have their explicit expressions, what's the next task? Now it becomes more automorphic. Oh, there it is. The second broad step in their paper. Yes, my name is Jan, by the way. You can just, yeah.
Whatever is the definition of p delta, can you restate the summation,
sorry, the summation? Yeah, this is the sum over all equivalence classes of quadratic forms with discriminant delta. Yeah. There's finitely many equivalence classes. This is a finite sum. And that gives me a finite sum here, which is taken as a, so these are divisors on the curve, and I view this as an element in the Jacobian.
I have questions.
Yes?
What is p-adic?
Sorry, what is?
The second term in the summation.
This one?
Oh, okay.
Ah, this is the logarithm, sorry. Yeah, this is my handwriting. So log of q. Yeah. So it's just the logarithm of the prime number q. Yeah. Okay. All right, so now the first time a modular form shows up. And it's a bit of a doozy, this modular form. But it's explicit. Like everything in Gross-Zagier's paper, everything is explicit, but not necessarily pleasant. So, but it works, and that's why it's a deep theorem, right? I mean, you have to do some very difficult calculation. But, okay, so what they do is they make a construction, and if you read that letter that I showed you yesterday, I showed you the first page, but if you read on, it contains precisely the details on this construction. So a certain modular form will be cooked up, which falls a little bit from the sky at this point, so you don't have to try and conceptually understand where it comes from just yet. But they make a generating series for these height pairings in a way that I'll make explicit later, starting from a real analytic family of Eisenstein series. Okay, so let's build this up in a couple of steps. So we have our two imaginary quadratic fields, K1 and K2. They're distinct. They're both imaginary extensions of Q, like so. And so they define a biquadratic field that contains both of them. Now, a biquadratic field will contain a third quadratic extension, and that quadratic extension, in this case, is necessarily real. Yeah? It's a real quadratic field. So if this is Q adjoined the square root of delta 1, this is Q adjoined the square root of delta 2, this is Q adjoined the square root of delta 1 times delta 2. Yeah? And because delta 1 and delta 2 are both negative, their product is necessarily positive. So this is the field diagram that is relevant. Now, F will be the magical key role player in the construction to follow. So what they do is they construct a Hilbert modular form over F, in the sense of Jada's lectures yesterday, except they won't be holomorphic. So they'll depend on some parameter S, but they do have two variables. It's a Hilbert modular form over a real quadratic field. And what it is, it's something completely explicit, but somewhat unappetizing at first sight, even though it is actually quite nice. So what they do is first they take a sum over the class group of F by taking some ideal representatives for it. Yeah? So F can have some big class number, but we sum over all of the class representatives the value of the character chi at this ideal, where chi is the character that cuts out L over F. Yeah? So this is sometimes called the genus character. It's a character of F. So it takes as input such ideals, and it spits out plus or minus 1, depending on what the prime factors do in this extension, whether they're inert or split. Yeah? That's what this chi does. Okay, so then they're going to take an ideal sum over the elements of A, and to make that well defined for the equivalence class, there's some innocent factor, norm of A to the power 1 plus 2s, but you can ignore that, that's not very important. What is much more important, and that's why there's a letter E on the left-hand side, it's an Eisenstein series, so it's an explicit ideal sum, and the explicit ideal sum is the following. So I'm going to take pairs of elements of the ideal A multiplied by n, and I'll tell you in a second what n is, times A. In fact, I'm now afraid that you won't be able to tell the difference between my Roman n and my German n. So I'll change my German n font slightly, and I'll just do it sort of a curly n, yeah, to avoid confusion there. Okay, so I'll take pairs of this A times A, and A, I've already told you what that is. That's some ideal that I'm going to let range over all of the representatives of my class group. And N is an ideal that I choose in F whose norm down to Q is capital N. And there's a choice involved there. It doesn't matter all that much which choice you make, but that's what this N is. Yeah? Okay, and now you also have to quotient out by the units. So there's a diagonal action of the units of F. That's a group of rank 1 acting on both factors simultaneously. And now I have my index set with my elements M and N. Okay? So index set is already complicated enough, and I haven't even started writing the lattice sum. So what I want to do, and what in fact Hecke wanted to do about 100 years ago, is construct this series and construct something of weight 1, 1. And if you construct an Eisenstein series of weight 1, 1, you always have to be extremely scared about whether it converges or not. Yeah? In fact, we saw that also happening yesterday. We may have to regularize, and that's exactly what Hecke did. But he regularized in a slightly different way. So here, what I'm going to do is I'm going to take M1. What does M1 mean? Well, M is an element of this real quadratic field, so it has two embeddings into the real numbers. Yeah? One I call M1, and the other I call M2. So I fix my two embeddings once and for all. And then I take M1 here to be my notation for the first embedding of M. I multiply that by the first variable, Z1, in the first upper half plane. And then I add N1. And then I do the same for the second embedding. So M2, Z2 plus N2. So this is what I would like to sum. Unfortunately, that doesn't converge. Yeah? This will be what an Eisenstein series of weight 1, 1 might look like, but it's not going to converge. And so the way that Hecke regularized it is by introducing what is now called Hecke regularization, this factor which takes the imaginary part of both variables, multiplies it together, and takes it to the power s. And then dividing out by the absolute value squared of these, also raised to the power s. So that's m1z1 plus n1 raised to the 2s, and then m2z2 plus n2 raised to the 2s. Okay? And that's it, finally. Yeah. Yes? Oh, yes.
What was the role of the capital N?
The role of the capital N, I also swept under the rug a little bit before. It doesn't matter all that much. It's to do with the fact that if n divides a, the first coefficient of the quadratic form, then b, the second coefficient, is a canonical square root mod n of the discriminant. And that choice, somehow there's a choice. Yeah? And so that's the same choice as this ideal n, in a nutshell. Yeah? So changing that choice will change the ideal n, but it doesn't really matter. And in fact, you can take the sum over all possible n's, and it wouldn't change anything. It would just introduce a power of 2 in all my expressions. So it's a fairly innocent choice. Yeah. Yeah. Yes?
Could you, I am actually finding it a little hard to understand what exactly this curly n times your ideal segment.
So this is pairs of elements. M will be inside of A and inside of N. So it will be in the product of the two. And N will just be in A. And then I take such pairs and I modulo out. So I take the quotient by simultaneous multiplication by a unit in F. So diagonal action of OF. If I don't do that, then it's hopelessly going to diverge. Here at least we have some hope. Still wasn't good enough. We still have to do this regularization trick. But with both at the same time, it now defines a modular form, because I haven't told you yet why I made such a bizarre definition. I didn't make it, by the way. Hecke made it a very long time ago, 100 years ago.
A priori and some ideals, but some they're not integers.
So no, they're not integers. They're elements of F. Okay. Yeah, exactly. So that's what. So M1 is the first embedding into the reals of that element of F, and M2 is the second embedding, and M1 and M2 in general will be different numbers.
The summation over integer ideals in OF, are you taking arithmetic in class group?
Yes, exactly. So I take my A here, and of course all of this seems to depend on the choice of A. It's not well defined up to. But if I change A by a multiple of A, so that they're the same element in the class group but different representatives, then all of this, you can check, will change precisely by the scalar that cancels out with this. So the norm of A raised to the power 1 plus 2 as the 1 coming from here and then the 2s coming from here cancels out exactly that dependence. So it seems like it depends on the representative, but it doesn't actually. Yeah. Yeah. Yes?
So you say the character is Jean's character that cuts
Yes.
out
L over f.
K1, K2.
No, it cuts out L over f. So it's a quadratic character of f, takes ideals and it spits out plus or minus 1. And for prime ideals, it'll spit out plus 1 if the prime is inert in this extension. If it's split in this extension, and minus 1 if it's.
Depends on K1 and K2 on the factorization.
Yes, absolutely.
So it's really the character that cuts out at K1.
Yeah, so the character knows indeed about K1 and K2 because it knows about L and therefore it knows about K1 and K2. Yeah, absolutely. Yeah. So that's in fact equivalent data. A genus character like so is just the same as giving a factorization of the discriminant as a product of two other discriminants. And that's exactly what the situation is here. Yeah. Okay. All right, so I haven't told you the punchline of this bizarre definition. And the punchline is that this is a modular form for the subgroup gamma 0 of German n inside of SL2OF. So the Hilbert modular group of weight 1, 1. And in fact, these things you can check. However, because of the appearance of this parameter s that I've put in here, this is not a holomorphic form. You can see absolute values appearing. This is going to be a smooth form. So this is not holomorphic. However, what Hecke was hoping is that as s would approach 0, this term would kind of go away, and this would give me a regularization of the specialization to s is equal to 0. That is a holomorphic modular form, and that's exactly what Hecke was banking on. So he's going to take the limit as s goes to 0 of this expression and construct a holomorphic Hilbert modular form of weight 1, 1. Except he made a sign error in his calculations, and if you take that limit as s goes to 0, this whole thing vanishes. So he constructed the 0 form. So that's bad luck for Hecke, but it's good luck for Gross and Zagier. So they exploited this fact in a crucial way. Okay, so at present, you're not supposed to really understand where this comes from. It's a bit of a deus ex machina, but let me tell you what Gross and Zagier did with it to connect it up with point 1 that I'm just erasing now. Okay, so when s is equal to 0, special value of this smooth family of modular forms, we have that E sub s of z1, z2 is actually identically 0. Yeah? So it's not a very interesting holomorphic specialization at all. Gross, Kohn, and Zagier, and Gross and Zagier first, actually, in a different setup, say, well, that's great. If it's 0 when s is equal to 0, I can just expand this thing as a Taylor series in s, and now look not at the specialization at s is equal to 0, but at the first order derivative, so the leading term in the Taylor expansion. So more explicitly, they do the following. So you take this family ES, and we're going to apply 3 operations to it. The first is we're going to set both of the variables equal to each other. Great. So now I get a smooth family of modular forms of weight 1 plus 1, which is 2. Okay. Still suffers from the same drawback, of course, as this. When s is equal to 0, it's 0. But Gross and Zagier say, well, now take the first order derivative of this family with respect to s and specialize that at s is equal to 0. So that's the leading term now in the Taylor expansion because the specialization vanished. This thing is, of course, not necessarily 0, and in fact they show it's usually not. And what it is now we have a modular form, smooth modular form of weight 2. So this is a smooth modular form. So C infinity of weight 2 on gamma 0 of n, and this is no longer a German n because I've taken the diagonal restriction. But I would really like a holomorphic modular form, not a smooth one. So what they do is they compute the holomorphic projection of this form. And the holomorphic projection seems like a scary thing, especially the computation of it is scary, but the definition is quite benign. If I take this smooth modular form, there's a meaningful way to compute the Peterson inner product of it with any holomorphic modular form in this space. So it gives you a finite set of numbers if you pick a basis for the space of holomorphic forms. And the holomorphic projection is the unique holomorphic form that has the same Peterson inner products with all of the holomorphic ones. So it's a very simple definition, but the computation of it, by God, that's very, very complicated. But that's exactly what Gross and Zagier compute. So they do these 3 steps. They write this thing down. It's horrible, but it's explicit. And then they do these 3 operations. They put the variables equal to each other, they differentiate s is equal to 0, and they compute the holomorphic projection. Some horrible expression comes out, but lo and behold, it's an expression they recognize from point 1 of their paper. Namely, the expressions that come out are precisely the expressions for the neuron height pairings of discriminant delta 1 and delta 2, shifted by the nth Hecke operator and then collected together into a generating series with respect to Q. And in fact, this series has no constant term. It's a cusp form. So this now, after this holomorphic projection, has now become holomorphic. And it's an element of S2 gamma 0 of n. Okay. Sorry? Yeah, this is the holomorphic projection. It's the thing I described in words with the Peterson inner product. Okay, so, and this theorem, it's a very deep theorem because there's no real conceptual explanation for it except they calculated both sides and they observed that they were the same. That's why it's a deep theorem, right? We know it's true, but we still don't really know why. Now, why is this useful? Because you see on the right-hand side, we have these height pairings, which we really love to know something about. And on the left-hand side, we have something related to a family of Eisenstein series. So this is perfect for the method of Rankin-Selberg. And that's the 3rd step in their proof, which will not be of great importance for us in this course, but nonetheless, I might as well mention it, because that's how they got their theorems. Is that, well, it's an Eisenstein series, so it's an infinite sum of things. If you take the Peterson inner product with a classical modular form, you can unfold. There's a standard unfolding trick. It's called the Rankin-Selberg method. And it's that they realize this modular form, which, let's give it a name. Let's call it F. They realize F as a kernel function. In the following sense, they prove that if you take F and you take the Peterson inner product with some holomorphic modular form in this space, out comes some number, and that number is actually up to some explicit constant equal to the first derivative of the L function of F at 1 times a certain geodesic integral, which I won't define what that means, but it's an integral over a sum of geodesics, depends on the character, of the form F z dz. So that's what they prove. And this gives you the connection with the L function as the part that is interesting for BSD, and it gives rise to all of the applications that I mentioned before. I'm mentioning it here even though we're not really going to need it, because of course for Gross and Zagier that was a key step. Nonetheless, we'll focus on the first 2 steps in the real quadratic setting, and I wanted to give you a little bit of a flavor what happens in that work. Okay. Yes?
About this computation in the first.
This one?
Yes.
Yes.
I can see why delta 1 and delta 2 appears in the ES, the Eisenstein's function.
Yeah, so the choice of delta 1 and delta 2, as Gonzalo was pointing out earlier, it's really kind of the same as the choice of the character chi. And chi appeared prominently in the definition of ES. So both sides know about delta 1 and delta 2, even though my notation does not reflect it. Chi is somehow the key ingredient here that gives you delta 1 and delta 2 on the left-hand side. Yeah? All right. Okay, so let's look at a particular case. All of this was, of course, very general. But what happens when n is equal to 1? Then things become maximally concrete. So in general, it's extremely general. We're on x naught of n, and we're dealing with modular forms of level n. I'm saying we're now going to specialize to the level 1 case. And of course, in the level 1 case, what we have is we have now an expression for p delta 1, p delta 2, Néron height pairing on the Jacobian. And by their point 1, this is the same as minus the log of this g thing, which I didn't tell you what it was in general, but I'll tell you what it is in level 1. In level 1, it's precisely the norm, down to q, of the difference of two singular moduli associated to this discriminants delta 1 and delta 2. And because I'm taking the norm, it doesn't matter which tau 1 and tau 2 I am taking. Yeah? So this is the log of the norm of the difference of these two singular moduli. So this Green's function, it's really just a difference of two j functions in this very particular case. Yeah? Okay, so they also get explicit expressions for the MQs. In fact, I was going to give you the explicit expression, but I'm out of time, so I'll do that when I get to it in the real quadratic case. And so what we should note is that these are explicit, and they're counted in this quaternion algebra that I mentioned before. So BQ infinity, it's definite. These are the differences of singular moduli that Zagier was factorizing on his trip to Japan, which I showed you last time. Yeah? So the j function here, we should note what's important about it is that in this case, when n is equal to 1, the modular curve x of 1 is isomorphic to a projective line via the j function. So j defines a uniformizer really on this genus 0 curve. It's an isomorphism with p1. And on the left-hand side, if you add these two up, both very explicit, this is a quantity we care about. These are explicit numbers times logarithms of q. They add up to the height pairing of these 2 points. Now, what's the height pairing of these 2 points? Well, I'm working on a genus 0 curve, so there isn't a whole lot of Jacobian to work with. The Jacobian's trivial. So this height pairing is also trivial. So this is equal to 0. And that's because x of 1 has genus 0. So if we stare at this, then what do we get? We get log of this quantity we care about plus log of some explicit integer equals 0. So then I just bring this one to the other side, I exponentiate, and I get a formula for the norms of the difference of singular moduli that's completely explicit. And that's exactly what happens in the first paper of Gross and Zagier, where in fact this leads to 2 completely independent proofs. Yeah? You can make this observation first and then say, well, the height pairing is equal to 0 because for geometric reasons this is true. Or you can follow Zagier's argument with this automorphic function ES and just observe that in the end you construct something on S2 gamma 0 of n. When n is equal to 1, that's the 0 space, so therefore the height pairing is also trivial without any recourse to geometry. So they gave sort of 2 independent proofs of that. What's remarkable is that the first proof, using this MQ and this counting argument in BQ infinity, relies on the moduli interpretation. It relies on the theory of CM elliptic curves. The second proof does not. It never makes use of the fact that J of tau 1 is algebraic or anything like that. So it's kind of powerful. And so these 2 independent proofs, and particularly the independence of CM theory of the second proof, will be hugely important in what is to follow. Okay, so let me just end with a question. And the question is, with this sort of quick and dirty introduction to some of the ideas in Gross and Zagier, the burning question that we would like to answer is what can be said, if anything, when these 2 discriminants that I picked, delta 1 and delta 2, are no longer negative, but are positive. For real quadratic fields, many of the elements that we've used in these proofs will break down. And in fact, it's not even clear how to make sense of such a quantity like singular moduli. And that's the question we will turn to next. And we'll see some of the elements in this proof come back later on. So I hope it was a bit more maybe highbrow and giving an overview of conceptually some of the steps in Gross and Zagier. Don't worry too much if the details seem elusive. It was just to give you a bit of an idea of some of the ideas that will come back later on. And in fact, next lecture will be a clean start. And if you haven't followed any of what I've said, that's great. You can start from scratch, and I will define for you rational co-cycles, and we'll get sort of a fresh start starting in the third lecture. Okay, see you tomorrow or next one.
Thank you very much. Are there some questions for the speaker? Yeah, I see it first. Sorry.
Just to like confirm, so here your capital N is dividing both the discriminants delta and
No. So capital N will not have anything to do with delta 1 and delta 2. No.
oh.
Yeah, I didn't state that actually, but
Just initially, like when we were just considering one delta, we were making the assumption that it divides delta.
it divides A. Yes, indeed. Yeah, that's an important difference. Yeah.
Oh, so the
So if it divides delta as well, then it's got to divide B as well,
oh, right.
and then
So whatever A1 and A2 are, so N will divide A1 and A2.
Say again.
So delta 1 and delta 2
Yeah.
associated with them will have corresponding A1 and A2, and thus capital N divide both A1 and A2.
Both what?
A1 and A2.
Even an 8?
A1 and A2. So
Yes, indeed, yes, it will. Yeah.
okay.
Which of course in this case is no assumption, but in general, yes. So N will divide, as this will both be Heegner points, so they're constructed through these Heegner forms. Yeah.
Right. And
That satisfy that condition.
so like when you took this, I don't know, double Eisenstein series and
Yes.
used a modular form of weight 2 for gamma 0 of N, is that reflective of like a general picture, like a map from
Yeah, it's a bit mysterious. I don't know if I have a good answer to your question, which essentially was maybe where does that construction come from? And I think it's a bit of a mystery. There are slightly more conceptual explanations, but in the end of the day, we have to be honest and say that it's a bit of magic. Yeah. And precisely the reasons why Zagier thought of writing down this series is also a little bit mysterious, but he was very familiar with the classical work of Hecke, and he was a master of these kinds of computations. And so for him, I think the starting point was probably this series. He started manipulating it, and he noticed that these J functions came out. And who knows, right? But yeah, it's a bit of magic.
Thank you.
Thank you. So I just realized it would be good to have a microphone for the people asking,
Yeah.
so that everyone can appreciate the answer to the question.
Sorry, that's a very generous way of phrasing it, but I can try and repeat the questions. I should do that, I think, yeah.
Is there a similar theory for works for CM field?
Yeah, so for CM fields in general, definitely, yes. And in fact, this whole business, it's become a big business in some sense, where all kinds of generating series of arithmetic pairings between algebraic cycles on Shimura varieties are being constructed, and their modularity is shown. This is called the Kudla program. And so it's a huge web of sort of results that vaguely all have the same kind of flavor. The work of Gross and Zagier still has an extra punch compared to what one can say on more general situations, and that extra punch is this application to BSD. And it's that extra piece of arithmetic coming from this pair of quadratic fields, etc., that gives it this arithmetic twist that in general you don't see for general statements. But the modularity of these generating series it's a huge program. Yeah. It's a Googleable program. It's called the Kudla program. So.
There was a question. There were two questions. I think let's start on the
Yes.
Could you describe a bit more precisely what the MQs are?
Excellent question. So the question was, could I say a little bit more about what these MQs are? Yes, I definitely can. I'm debating whether I should do it in my talk, because it takes a bit of time, or whether I should do it in the break just with you on a board, or whether I should do it right now. Given the time, maybe the last option is not the best option. Yeah, it's a purely algebraic description. Let me just say something qualitatively that counts pairs of embeddings of the maximal orders in these two quaternion algebras into a maximal order, in these two imaginary quadratic fields into a maximal order of this quaternion algebra. And it counts them up to simultaneous conjugation. And for every such pair of embeddings, you measure how congruent the image is modulo Q. And then you add that all up. And at the end of the day, you get a finite tally. And that tally is exactly what this MQ is. So in a nutshell, that's what it is. But I'm happy to make it more precise in the break with you or during my next or final lecture. Yes.
So maybe let's hear a last question. Maybe after, you can also ask in the house.
You have described the tau and the divided. What is exactly tau 1 and tau 2?
Yeah, here it doesn't really matter. So tau 1 and tau 2 will be CM points of discriminant delta 1 and delta 2. And which one you take doesn't matter, because if you take a different tau 1, it'll appear as some other factor inside of this norm. Because the norm, by the Shimura reciprocity law that I said before, will essentially just be the product of this expression where tau 1 and tau 2 range through all the possibilities. And if you write it in that way, you see that it's independent of the choice you make.
Thanks. Maybe more questions in the pause, and let's think again, Jan.
Just a quick question.
Yeah.
So this is with the Heegner form and dividing A. Does this have something to do with the Heegner hypothesis?
Yeah, it's exactly that.
It is
the
okay.
fact that you can find such a form
Right.
implies that all the primes dividing n must be primes that split in Q adjoin square root of delta 1.
Yeah, I'm not very
You see,
familiar
because,
with quadratic
well,
forms.
Para que ahora hay que tener cuidado.
No pasa nada.
Nachito, sí, sí, así mismo, mira. Ahí.
Perfecto. Vale.
Ya, perfecto. Y está un bolsillo ahí escondido en alguna parte que no le moleste.
Listo.
Ahí están los plumones.
Listo, listo. Tac, tac, tac. Sorry, should have made sure this better.
But yeah, make me remind me.
No, but you can say it now.
Yes, true. So, yeah, maybe before I forget it after the talk, but I will hope I will repeat it. So for the asado, for the barbecue tomorrow, in case you haven't yet, you can sign up with Luis Santiago. Here's here in the right corner, front corner. And you can also say if you're vegan, vegetarian, like fruit preferences, whatever. So that this will be respected. And then welcome back and welcome to the first class of the course from Juan Rodriguez on condensed mathematics, and I think we get right into things.
Okay, thank you very much for the introduction, and thank you very much for the organizers to invite me to give to visit Chile for the first time and to give a talk in this wonderful summer school. So today, well, at least in this fourth series of lectures, we'll try to explain a little bit about what condensed mathematics is about. Condensed mathematics is a theory developed by Dustin Clausen and Peter Scholze around 5-6 years ago, I would say. Maybe it started a bit earlier in 2018. I like to think that the condensed mathematics came up, in particular because of some necessity of solving a long-standing inconvenience
in mathematics, which is mixing algebra and topology. So condensed mathematics, you can think about that as a playground where maybe three areas of mathematics interact in a very clean way. So these ones are analysis, topology, that maybe these two are more clearly related, and algebra. So again, this is just a place where these three areas or subjects play a role. It's not necessarily saying that this one contains all of them. It's not that what condensed mathematics is about. It's just a place where you can make interactions between these three in a, again, in a very elegant and, I don't know, we'll say intuitive way somehow. So of course, condensed mathematics is not the only thing that they develop. I would say that the main application of condensed mathematics that they have is to analytic geometry. So within the realm of condensed mathematics, they also make some kind of geometric theory, which allow them to pass, well, from just, let's say, the promotion of topology and sets to condensed mathematics into a thing that they call the analytic stacks. Which is, again, some world that aim to generalize basically any existence theory of this that appears in practice that involves analytic geometry, algebraic geometry. So this will include, for instance, things from algebraic to just usual algebraic geometry. Will sit inside here. Also, I don't know, complex analytic geometry. Sitting here, things like rigid geometry. Or adic spaces. Also will sit in here, smooth manifolds, differential geometry. And I will explain what actually this means, maybe. It's sitting here, and there's a usual topological space as well. And okay, maybe this looks a little bit pretentious, but this has a concrete mathematical statement: is that well, all these setups, what you end up studying is just some particular categories of geometric objects, in algebraic varieties or complex analytic varieties, rigid varieties, differential manifolds on topological spaces. And analytic stacks that they will contain all of them, basically fully faithful, at least. So it's just a world where you can just embed all these existing geometric categories into the same world, and then you can start comparing them just because they live in the same world. So there is no need to make some kind of construction here. So in this series of 4 lectures, the idea is to maybe, well, first explore a little bit of what condensed math is, like this definition of condensed sets and so on. I mentioned some kind of first interesting property that you can make just without appealing to geometry, or at least not through analytic stacks. And perhaps at the end, maybe the second or the fourth lecture, to mention a couple of applications that one has once start pushing towards this side of the picture. Like, well, I'd say that so far most applications in arithmetic geometry, I would say. Okay. So, in order to motivate the definition of condensed sets, of condensed mathematics, let me first address well, the classical problem that we find in topology and algebra. So classically, algebra and topology. Well, these do not mix well. So what I mean by this is, well, we have algebra. For example, we have abelian groups. Abelian groups, well, this one forms an abelian category. But if we start to mix topology into the picture, something that we do every time that when we do for example, Frechet spaces, Banach spaces, and so on, is just trying to mix algebra and topology in some kind of algebraic structure that has some non-trivial topology. Then, well, we end with the category of topological abelian groups. Which is not an abelian category. So, in order to apply, let's say, more sophisticated or complex techniques coming from homological algebra or category theory, this is really inconvenient because we cannot just treat topological abelian groups as we will do with just usual abelian groups. So this is something that is classical. So we'll say that a prototypical example of this pathology is the following. So consider the real numbers with their natural topology. But, well, this is the way we look at the real numbers whenever we do, let's say, analysis. But let's say that we just want to do algebra at the same time. So when we do algebra, we don't care about the topology of the real numbers. We just care about the fact that it's a field. So we can also consider the real numbers with D with a discrete topology. We have a map. Maybe want to try to not make use of this down part of the board because maybe people down in the back cannot see very well. So we have a map and a continuous map. From the discrete real numbers towards the usual real numbers, for which, at least in the category of topological abelian groups, well, you still can define what a kernel co-kernel is, well, still has a zero kernel, zero co-kernel, but basically because they have the same underlying points. Zero kernel. So in usual algebra, this will mean that these two are the same, but they're not, because of course the topology just are different. So that's a problem. So this is a problem. Basically because, well, you just say we've got this equals equal to 0, and I would like this not to be equal to 0 because these two spaces should be different. And then you may wonder, okay, but why do you even care about this quotient? And that's a fair question, but I will say that actually people care about this quotient. So why do we care? So for that, let me maybe mention the following. These two spaces are not like arbitrary spaces. At least, well, this one is just a discrete space, and this one is maybe a metrizable space. So in particular, you can test continuity from functions of metrizable spaces just by looking at sequences. Right? This is the way we learn how a continuous map from the real numbers to something is continuous. It's just that a sequence that converges is mapped to another sequence that also converges, like the usual, more classical definition. Yeah.
So What is explicitly the map from RT to R?
It's the same map on underlying points. It's just saying that this map is continuous. It's just saying that the identity for the real numbers is continuous from the discrete topology to the usual topology. This is because here the open subspaces are any subspace. So any map that you put here, the pullback is going to be open, no matter what you do. So for that, well, let me consider the space that parameterizes sequences that converge. So this is something that is easy to draw, and maybe easy also to just write. So it's this kind of funny, like one-point compactification on the right of the natural numbers that you can imagine just as having things that get closer to infinity. With the topology that, well, you put basically neighborhoods of infinity are just all but finitely many natural numbers in infinity. So the topology put in here. Then given X a topological space, let me just call it topological space by top. Then continuous maps, which maps going to be continuous, maybe 0. To here that I'm going to keep denoting just by X in infinity. What are there? Well, there are just sequences of points in X with a convergence point, which is fixed. And maybe, well, if your space is Hausdorff, then as long as this converges, it's going to converge to a unique point. But in general, for a random topological space, telling you to which point it converges is actually additional data you need to specify. Like there are no Hausdorff spaces that you can converge to two different points. Right. Okay, so we do care about convergence sequences. So let's just plug that to this quotient before taking the quotient. So then consider. So there, the thing that we did is just first like taking the quotient, and then maybe we get a topological space. But let us just first take continuous maps and then taking quotients. So I can take the real numbers at this thing, and then take these discrete numbers and add this thing. But now what we get is non-zero. And actually, if you look what it means, well, this is just sequences in the real numbers that converge. Which is a vector space for which you mod out by the sequences which are locally constant. So another way to say what this is just basically tails of convergence sequences. And this is what we study whenever we want to understand what is the rate of convergence of a sequence going to a point, for instance. So these are objects that appear when we do analysis, and it's encoded by this funny quotient of two spaces that you would not like to take the quotient classically. So we care about this, at least if we just change a little bit the language. So, well, what is happening here? Well, what's happening here is that if we take the quotient in the most naive sense, this is not going to work because, well, again, topological abelian groups is not a abelian category. But instead, we should try to rethink the way we see topological spaces. So, for that, let me just recall maybe what's going on. Okay.
Some connectivity issues.
Okay. So recall Grothendieck. So what did Grothendieck teach to us is that, well, we should not look at objects whenever we're trying to study some kind of mathematical object. So do not look at objects. A better way to study some mathematical objects is by looking at maps between objects. And somehow we do that implicitly whenever we study topological spaces, at least for instance some kind of topological spaces. When we study like differential manifolds, well, we don't look just at the manifold as it is. What we always look in mostly is kind of the differential functions of the manifold, the smooth functions of the manifold. And this is just looking maps between the manifold and the real number. So we're always looking maps between manifolds and other manifolds and so on. So this is something that, well, we always do implicitly, but maybe, well, Arithmetic, let's say, make it a more categorical way to address these kind of things.
I'm sorry.
Yep.
What is exactly a locally constant sequence?
It's just a sequence that is eventually constant.
All right, eventually constant.
Yeah, sorry, I should say locally, I should say eventually. Thank you. Thank you. Sorry. Thank you so much. Eventually constant. Yep. Well, so for that, again, maybe in order to solve this problem, so something we can do. So for solving this issue, a way that we know how to make differences between spaces is by just we could look not at the real numbers or the discrete real numbers, but at the collection of maps from X to the real numbers, from X some kind of topological space. So by kind of just categorical phenomena, if we apply Joneda, like we know that a way to make a difference between this space and that space is just by looking at all these possible maps. Like if we know all these possible maps, well, we kind of just already over-determine this space a little bit too much. So maybe just looking at all this collection of maps for all topological spaces is too much, and we don't want to do that because there are just many weird topological spaces. So we would like to just isolate a nice class of topological spaces which are enough just to distinguish, for example, these two guys. So distinguish a class of reasonable topological spaces. So this is too much. But we just care about at some X in top enough to distinguish, let's say, reasonable topological spaces. And again, the motivation for this was to mix algebra, topology, and analysis. So, well, of course, reasonable doesn't have a mathematical meaning, but at least for this idea, reasonable will refer to spaces that occur in analysis. Which again is also not well defined, but a little bit gives a better idea than reasonable. Okay. So spaces that we would like to be, let's say that for maybe historical reasons, or maybe just because of all the kind of spaces that show up in analysis, like Frechet spaces, Banach spaces, or maybe in more geometric aspect of analysis, like CW complexes, differential manifolds, and so on. A class of topological spaces which is rich enough to determine many of these spaces are just compact Hausdorff spaces. So reasonable class. Are compact Hausdorff spaces. Let me just call it like that. So this is, let's say, because well, there is some. So, for example, let's say that if I don't know, V to W is a map, let's say, of Banach spaces. But not necessarily continuous yet, then F is continuous. If and only if, well, I think that it's enough just to test at sequences because I have metrizable spaces, but let me be a little bit more over-determined for all compact Hausdorff space. Maybe also here's. And any map from C to V, continuous map, the map F G coming from C to W is continuous. So whenever you have a map between these guys, so I mean, this I could just change Banach spaces by metrizable spaces. It could be to be the same. I should just put metrizable actually. You can test that something is continuous just by precomposing with continuous maps from just compact Hausdorff spaces. Like again, this metrizable, you can just take sequences, that's enough. But I want to over-determine this a little bit more. So these kinds of spaces that can be determined by compact Hausdorff spaces is what we call the compactly generated. Because, well, by kind of definite construction, they are generated by compact Hausdorff spaces in some sense. And any space at period analysis is going to be compactly generated, at least if you do reasonable analysis. So, okay, we have compact Hausdorff spaces. But now there are also many maps between compact Hausdorff spaces that kind of determine each other. And this is one of the first exercise, or I don't know, I don't know first, but some exercise or some proposition or lemma that one encounters in just usual point set topology class, which is the following proposition. So let maybe C1 to C2 be a surjective continuous map of compact Hausdorff spaces. Probably just mess up this S. So then F is a quotient map. So this means that if we have a C1 and we model by the equivalence relation given by the map F, well, this map actually presents C2 as a topological quotient of this object C1. And maybe these are F. It's just given by C1. This fiber product sitting inside the equivalence is just an equivalence relation inside this product. So, well, if we are trying to test, to use compact Hausdorff spaces to test, let's say, continuity of differential spaces, then many of these maps, whenever they are surjective, they're going to be over-determined. Again, because you can just compose with these ones and be in a quotient base that we can always replace such a map by something that is going to surject onto this. So, okay, Okay, that's a thing. And well, like maybe working with all compact Hausdorff spaces still is not that easy because there could be like very strange compact Hausdorff spaces in nature, like mix of things that you can maybe not control very well how continuous functions look like. Well, maybe I would say something strange, but even the interval 0, 1 continuous functions are a little bit weird, like something that you cannot just write down. You don't exist, but they're not like formulas telling what they are. So we would like to have like a class of compact Hausdorff spaces that somehow are the easiest ones, at least from an algebraic point of view. Because recall that the motivation is to make a mix algebra and analysis and topology in the same place. So we want to make this as simple as possible, at least from the algebraic perspective. So maybe compact Hausdorff are still a little bit complicated.
Can you explain what is Arithmetic?
Can you say as well? Sorry?
Arithmetic.
It's just an equivalence relation. Sorry.
Okay. So it's not in direct product of C1 and C2.
Well, equivalence relation are inside the products of, C1. Oh, that was a huge typo. Thank you. Yes, just this equivalence relation inside the product of C1. Complicate. So we want to find at least we know that we can always replace a compact Hausdorff space by anything that projects onto that, at least for that kind of questions, for addressing when continuous maps are going to be continuous. So the idea is, well, whenever we have compact Hausdorff space, we would like to find like kind of the easiest spaces that are going to project into them. And it turns out that these spaces, well, for this maybe, let me just state another proposition. Oh, yeah, maybe, yeah. Before saying the proposition, let me just.
That example just relies on the fact that F is a map of many spaces, or it can be.
No, I think it's, yeah, let me just say metrizable, just to make it. I think that's enough. Yes, being Banach is not important. But any metrizable space, you can test the continuity in this way.
So in other words, you say that you're studying metrical space by just restricting to C-Hus, correct?
Sorry?
Hausdorff and compact.
Yes?
You are restricting your work to compact.
What I mean is that you can test that a map is going to be continuous by precomposing with continuous map from compact Hausdorff spaces. Yes, like if you had something compact Hausdorff going to V that is continuous, then if this composition is continuous for any possible such a map, then this map is going to be continuous as well. So at least to distinguish continuity between maps, these ones do a very good job, let's say. And somehow much simpler than a random metrizable space. I mean, you could also say metrizable spaces. So let's say some kind of proposition, maybe more like a lemma, is that, well, given a compact Hausdorff space, we can find a profinite set that may be S. We're going to just recall what this is in a second, but again, like Galois groups are just profinite groups, for instance, which surjects into this compact Hausdorff space. I recall that but profinite sets maybe denoted by prof inside compact Hausdorff are just particular kinds of compact Hausdorff spaces for which you can, well, define in different ways. you can define these guys as such that well, one of the following equivalence things holds. So this one, they are like as in here. This one is totally disconnected. Meaning that they are just the only connected components are just points. And another way to say this is basically that S is just the limit of finite sets. Limit. With the usual topology you put in the limit. Okay, so maybe, well, it sounds maybe a little bit weird because you may say that, well, maybe profinite sets look more scary than the interval. But I would say that they do not look more scary than the interval because you can actually just write down explicitly what maps between profinite sets are algebraically. So given two profinite sets, well, the maps, continuous maps between them, well, you can just write it down as the limit of J of a colimit of I of maps between finite sets. So indeed, just continuous maps, you can write it down as just a purely categorical construction, something that is just limit or colimits of just a finite set that you can just, well, finite set between maps between finite sets. So this says that at least this category of profinite sets is something that you could access through by using topology in this way, totally disconnected Koppe-Hauter spaces. But it's also a category that you can just write down purely using algebra or let's say set theory. And you don't need to appeal to any kind of topology anymore for defining this category, just by declaring the maps to be this. So maybe not to prove this, but let me just give an example of this phenomena that is something that we actually know since we are in, I don't know, middle school or something. So I really like this example. Well, so usually maybe the profinite nature, you find them more like when you do p-adic analysis. P-adic numbers is where they show up more often, but I will tell you that this is actually not true. So consider an interval 0, 1. And well, whenever you have a number here, the thing that we learn how to write these numbers is basically just by writing a decimal expansion with this point between maps between 1 and 9. And well, there is some kind of rule that we follow is that if at some point we have a bunch of 9s, well, this number is actually the same as just writing like this number like this, right? It just had something here. It's something that we just learned in school. Okay, so there is a more clean way to translate this. Is like precisely in the spirit of that proposition. So just consider the profinite set, which is the product of integrals from this by this between 0 and 1 and 9. Then, well, we have a map. So we have a map. from S to the real numbers, which is surjective, that what it does, it just sends a sequence of these numbers, well, to the decimal expansion. But let me maybe just write in this way. T to the n. And, well, this map is easy to check that it's a surjective map. Well, easy to check that it's a continuous map. So it's actually a quotient in compact Hauser spaces. And again, this is just an instance of this proposition that any compact Hauser space can be refined or surjected from a profinite set.
So when you write limit, it's kind of like the projective limit. So
Yes.
it's not the union, it's like...
No, this is more like the union.
Yeah, okay.
Yes. Yes, yes, yes. I maybe should write this or this. Yeah. So, okay. So what this proposition tells us is that, okay, instead of looking, so maybe we can restrict for the sake of trying to test when two maps are continuous or not, or to distinguish topological spaces, we can restrict to profinite sets. And now we're in good shape, because now we are in the world where somehow even though we started from topological motivation, we just came to pure algebra. And maybe algebra, let me just say set theory in this case, which are profinite sets. So in order to actually make the definition of condensed sets, or maybe something more condensed ring and so on, we'll need to still do a little bit more steps. So I really know that this one are going to distinguish a lot of different topological spaces, but we still need to construct them out from profinite sets in some clever way. And well, for doing that, so window these profinite sets, let's say with a growth topology, saying that a map with covers are generated by disjoint unions, finite disjoint unions, and surjective maps. So this is just telling us how we should identify the profinite sets, or compact Hauser spaces. We saw that, well, any surjective map is a quotient map, so we just should identify a quotient map with, like a map should be covered by anything that's surjection to that, because it's like a quotient of topological spaces. And then we can get to the definition. Condensed it's a functor, or it's a sheaf of sets on this category of the side of profinite sets. So let me write down more explicitly what this means. And well, this is just a condensed set, but you could make the same for a abelian group, ring monoid, and basically any algebraic structure. It's just a sheaf on this algebraic structure on profinite sets. So, more concretely,
but sorry, the sheaves are on the profinite topology, or?
In the topology, this is coordinate topology. So let me just write down concretely what this means. Yes. So let me maybe call condensate, the category of condensates. And an object in this category is the same as a functor from profinite sets, let's suppose it's category, to sets that satisfies the following conditions or the following properties. So the first one is that when you evaluate T at the empty set, well, you should just get a point. You should imagine that whenever you take a profinite set, T of S, which is just the points of S here, is basically corresponds to maps from S to T. So you should think about taking these S points as just taking the continuous maps in some codes from S to T, because this is at the end what we're trying to make more algebraic, just talking about continuous maps. So whenever you have a disjoint union of profinite sets, well, like a continuous map of disjoint union is just the map from here to here and here to here. So this one is just T of S1 equals T of S2. And the last one, which is more the shift property, says that, well, if you have a S1 surjecting into S2, then if you look at the S1 points and you restrict to the two projections, to the points in this fiber product, then well, so that this is an equalizer. So in other words, like, well, to construct a map from S2 to T, or a point from S2 to T, suffices to construct a point from S1 that is the same in fibers, which is again something that you will do whenever you do like a quotient of topological spaces. To construct a map from the quotient, it suffices to construct a map from the fixed thing that it just agrees the fibers. So this is what the shift property is here.
Does the shift condition already not guarantee?
Sorry?
Does the shift condition already not guarantee that this should be the case?
Sorry, I didn't hear the question. Is the shift condition the
In the definition, there is already the condition that it's a shift.
Yes.
So wouldn't that already guarantee this last condition that you have written?
Like this one is basically the shift condition.
Yeah.
I'm just trying to, I was trying just to say more explicitly what this means in terms of this side. Yes.
It's not additional.
Sorry, you're not requiring that the first map, condition 3, is injective, or it's inside the...
The three, phi in an equalizer tells you that like these points are precisely the points in here satisfying that these two maps are the same. So in particular, this map is going to be injective, p in an equalizer, yes. Okay, so we did these crazy definitions a little bit. Yep.
What is the codomain of T that you wrote it?
This thing, yes, sets.
Set.
Yes, this is a functor.
All right.
It's a functor. Let me not do that here, but maybe we can talk about after the talk. Yes, it's basically just a generalization of what unusual topology is, where you declare something to be covers and you want to, let's say, make some identification. Like for example, étale topology, something used in algebraic geometry a lot, is one instances of this kind of topology. Maybe one, kind of the main first examples that appear.
When did you make use of the definition of that?
It's precisely this condition.
It's implicit. It's implicit. Okay.
Yes, exactly.
If you had not mentioned it, then this would make sense.
Exactly. Yeah, thank you for that. So yes, the Grothendieck topology basically is going to translate into this third condition. Yeah, this is the condition that you just remember.
First condition is what exactly is this star here?
Well, there is only one map from the empty set to T.
All right.
Yes. Okay, so give this definition. So let me maybe go back to the motivation that we wanted just to make more algebraic topological spaces. And maybe just say that once we have this definition, well, we end up studying shifts on some site, so rotating topology. So basically, most of the properties that are satisfied by sets would also hold in condensed sets, just kind of abstract constants. So for example, we can take quotients, equivalence relations, I don't know, unions, products, and so on. Just in this world, without worrying about topology anymore, because this is just kind of taking things point-wise and maybe do some slight process afterwards. So let us compare with topological spaces. And let's see. So maybe the first observation is that we have a functor from topological spaces to condensed sets. A functor that, well, we wisely called the condensification functor. So this functor maps a topological space to exactly what you will expect to map after this here. So it takes a topological space, it maps to a functor for profinite sets that maps a profinite set to x of s that I recall that was the continuous maps from s to x. And we'll leave you to an exercise to verify that this construction actually gives you an object satisfying these conditions, where maybe the first two are kind of easy conditions, and the third condition is just expressing the fact that a surjective map between compact half-order spaces is a quotient map. Like if you try to write down what means, well, just to map from how to recover maps from S2 to a topological space from S1, this is exactly the condition you will find, like maps from here which just agree in fibers. So this functor, in its biggest generality, is not fully faithful, it's not an injection. You will say, okay, so there's maybe some topological spaces which are missing in here. But turns out that at least what is missing are maybe the weird topological spaces. And all of the spaces that we actually care in analysis, they are going to embed in this category. So for that, let me just state a theorem. So maybe the first one is that, well, technical is that, well, inside this, whenever you work in a shifts in a site, there is some internal notion of being quasi-compact and quasi-separated. That maybe let me not it's exactly what it is. You just for the expert is that if you look at the objects which are quasi-compact, quasi-separated, you should think about quasi-compact like some kind of analog of being compact in the more categorical terms, and quasi-separated as an analog of being Hausdorff. But these one are purely categorical conditions. Well, turns out if you do this with condensed sets, well, you actually get the same as this. Like this condensification functor, when you restrict to compact half-order spaces, this identifies with the quasi-compact, quasi-separated objects into condensed sets. So this means that at least the initial ones that we try to isolate to distinguish continuous maps, they can recover purely in categorical terms from condensed sets. So we know how to recover these ones. In the second one is that, well, maybe we cannot recover all topological spaces, but we can recover reasonable topological spaces. So I don't think this is a standard notation, but let me just use this. So this one, let be the category of compactly generated topological spaces. So these are spaces which are quotients of disjoint unions of compact Hausdorff spaces. Anything that you couldn't write down in these terms, and maybe it's a little bit strange, but things like Frechet spaces, Banach spaces, CW complexes, well, of course, profinite compact Hausdorff spaces as well. All of them belong into this category. So like a lot of usual things appear in analysis, they just belong to this category. So then, for these objects, this functor is actually going to be fully faithful. Not this. Okay. So this theorem is realizing the idea that we had before that, well, condensates, you will be able to isolate compact Hausdorff spaces from them. Like you can test something is continuous from compact Hausdorff spaces, and condensates are going to generalize reasonable topological spaces, where in this case, reasonable becomes precisely this category of topological spaces. So of course, you will not expect things like the Zariski spectrum of a ring, which is some kind of non-Hausdorff space, to show up in here. But this is because these compact Hausdorff, these spaces are not those that appear in analysis. They appear more in algebraic geometry when you try to study topologies, like Grothendieck topologies of rings, but they don't show up in analysis. Frechet Banach spaces, compact Hausdorff spaces, these ones appear in analysis, which was the goal in here.
Finite number of CIs or not?
Arbitrary of them. Now, this one is arbitrary, yes. So maybe as an exercise, I'll let you how to write down a Banach space as a quotient of these guys, which is interesting.
What means exactly faithful?
This would mean that, okay, it's a good question. Let me just say exactly what it means. So this means that whenever you have two topological spaces in this category, well, you can look at the continuous maps between them. But this space is going to be the same as the maps of condensates between these condensifications. In other words, there is no distinction between looking at maps in here or looking at maps in here from these objects. So categorically speaking, this means that this one is basically just a piece of this. So well, I think because I basically over time, let me just maybe say what will be the idea of the next lecture. So after giving like an idea of what condensates are, in the next lecture, the idea is to maybe give a little bit more of properties of condensates, in particular how condensed abelian groups naturally give you, for example, topologies between mapping spaces of topological abelian groups. For example, usually when you take two Banach spaces, there are, I don't know, like 10 topologies. I don't know how many topologies you can put in the mapping spaces, something like that. But we'll see that here there is going to be just one natural topology you can put. I mean, you can't consider the other ones, but there is one that is going to be natural, including this here, which is kind of the compact open topology, which shows up. Then, well, after exploring a little bit more about condensates, the idea is to give maybe a couple of applications, maybe one of with too many details. Applications that, well, kind of goes towards arithmetic geometry, which is, I think, that the main subject of the summer school and the conference. Right, okay, so let me maybe just stop here. Thank you very much.
Thank you. Are there any questions for Frank?
Do you have a description of the point rank from the left to the right?
Sorry?
A description of the factor, if you have any, from the left to the right?
From the left to the right, that's a very good question. Yes. So you have this functor from this top W going into condensed sets. And this functor turns out to have a left adjoint. Let me just write it this way, which maps a condensed set to something that maybe you call the point top, topological space. So whenever you have a condensed set, you can associate an underlying topological space. So what is this, the top? So this one is just again, the underlying points of T, just mapping from the points to D that give you a bunch of points. And the topology is the quotient topology coming from, well, whenever you have a map, let me say it this way. Whenever you have a map in T of S for S profinite, this is the same as having a map from S to T by Yoneda. And this gives rise a map from the points of S, which is just S, mapping to the points of this. So using these maps, you can just look at all possible S and possible maps in T of S. And this T top is just the quotient topology around these compact maps. So that's why you are also landing here. And well, compact half-order spaces you can just recover using this way. And in general, whenever you have an object in here, the way to recover this object from here is precisely via this procedure.
So using this map, can we end up in topological spaces that are not metrizable, for instance?
That's a good question. Yes. Even there are some profinite sets which are not metrizable. I didn't mention this here. Let's say that what I told you here was kind of the first foundations of condensed mathematics. Nowadays, there are slightly different foundations for which you restrict maybe not all profinite or compact half-order spaces, but just to those which are metrizable. And again, this is enough for many applications, basically any reasonable application that we have. So there is a way to kind of restrict the spaces that you will get something that is not metrizable, but close to metrizable, approximately by metrizable spaces.
Can you give an example of some condensed set which is not in the essential image?
Yes. This guy. I can tell you what the points are. Maybe that's more interesting.
I had a question to that one, but yeah. Okay.
I'm sorry. Let me just write it down again. So for example, this space, which was maybe the motivation talk, I should actually finish that with that. Thank you for the question. Is that whenever you take a profinite set, you can actually compute what these S points are, which now just makes sense to take the quotient in condensed sets, maybe in condensed abelian groups. And when you evaluate this as a profinite set, so the difference is going to be, well, here you get the continuous maps. Let me call that C instead of map just to make it shorter. From S to the real numbers divided by locally constant maps. And that's why we wrote before locally constant. So S is finite. This is just 0 because any map from finite is locally constant. But it's not finite, and these two spaces are different. So in particular, if you plug this finite space, you will recover the first part of just the tails of convergence sequence real numbers. Yes?
But also that we don't see geometric topologies such as the Zariski. No? You said that we have like analytics.
Yes.
So which part are we recovering? Like
So these sort of topologies, they came from, let's say that the word topology is maybe used in at least 3 different contexts. One of them is topology as an point set topology, maybe we do in analysis. The second one is maybe topology as we may think about in algebraic topology, when we just care about maybe maps up to maybe some kind of homotopical properties, so kind of. And the third one is the one coming from the Grothendieck side, which is this Grothendieck topologies and sites and so on. So the Zariski and the FPQC topologies are more from the third kind of the Grothendieck topology. This one is ought to solve an issue for the first kind of topology, which is the one on analysis, and maybe after doing a little bit more fancy stuff, you can also mix the second one. For going and relate with this kind of topology, you need to jump into geometry right now. So you need to jump from condensed mathematics into analytic geometry. And there's going to be a topology that shows up here that generalizes some FPQC and Zariski and et al. And many other kind of topologies that show up there.
Okay, one question. So I just had this, because I'm not so firm with the language of functors, I always forget. Is the first part of the statement like just the second part observing that you can describe the full image, or is there even a different? Is it the full subcategory when you write QCQS?
Right. Yes. So this one is yes. Thank you for the question. So you have condensed sets, just these functors, and QCQS is just some specific kind of subcategory here. So being QC, for instance, for
like a full subcategory.
It's a full subcategory, yes. So this one just means that there exists some profinite set and some kind of surjective map in the sense of, let's say, a shift in topology. Being QC, QS is that kind of, when you look at the diagonal map, and you look at any map from a profinite, so this product here, I don't know, just writing something, is prime. But this one is also a profinite.
Okay. I just want to see how stuff is contained in the compactly generated, right? That's a see how stuff in top.
Yes.
So it's in particular, you can describe the image. It's the point.
I think that the point is that you can reconstruct compact half-Dor spaces purely in categorical terms from condensed sets. Like, you have this, you have compact half-Dor, and I don't know, like, they actually land into here via this functor, and they're actually the essential image of this one here.
Yeah. So before we thank Juan again, I want to remind it again that to who hasn't done it yet, sign up with Luis Santiago for the barbecue tomorrow with your dietary restrictions and so on. Okay, let's thank Juan again.
Thank you. I think this belongs to you.